Good morning, good afternoon, and good evening, everyone. My name is Budiman Minasni from the University of Sydney, and I'm also the chair of the Scientific and Technical Committee of the 4 per 1000. Welcome to the 4 per 1000 Soil Carbon Science webinar. So today we have a very important topic that we want to cover. Well, modern agriculture, as you know, was built on available energy and synthetic nitrogen fertilizer. But today's rising energy costs, geopolitical instability, climate pressures, and supply chains has disrupted this energy. And now it exposed how deeply our food production depends on fossil fuels and the global fertilizer systems. This webinar will explore a question. Is there a role of soil carbon in agricultural resilience? Can soil organic matter be part of the solution? And the answer we'll explore today if we understand the mechanisms, the effect, and build on stocks that make the system more resilient. In this webinar, we will explore how soil carbon and nitrogen cycling can help us reduce fertilizer dependence, stabilize yields, and also protect farm livelihoods from the market volatility. Today, we have two distinguished professors who will share with us about their view and their research. And the first presenter is uh, Dr. Matthew Wallenstein. Matt is a soil ecologist, and his research is focusing on how soil microbes regulate nutrient cycling and soil organic matter. He was previously served as a professor and head of Department of Soil and Crop Sciences at Colorado State University, and now he is the chief soil scientist at Syngenta Group. His research is on advancing the understanding of microbial controls on carbon and nitrogen cycling. And he also has a role in translating soil microbiome science into agricultural innovations. And he is also a fellow of the Ecological Society of America. Over to you, Matt.
Thanks so much for inviting me today, and thanks to everyone online for joining us. Today, what I want to talk about is the role that soil carbon plays, not just as a climate buffer, but as a buffer to nitrogen fertilizer shocks and as a financial safeguard for farmers that depend on it. The path to soil carbon scale depends on not just identifying, but really making sure that the importance of soil organic carbon is valued by the whole system, recognized by farmers, and incentivized. So let's start with what just happened. We all know that right now, the fertilizer supply chain has been impaired by the shutdown of the Strait of Hormuz. And there's been a lot of media coverage of this, and people are worried, understandably, about the effects of a fertilizer supply shock that translates into high prices for farmers, and the implications of that for food prices, for food shortages. But typically, these supply shocks are short lasting. We'll see about this one. And we forget about them. At least the media forgets about them. I'm not sure farmers forget about them, though. And the question we want to explore today is, when does a fertilizer shock actually end? Does it end when the supply chain is normalized, or are the impacts felt for long after that? The shock doesn't really just hit the market, it hits the soil. And the soil has a memory of that event. So here's the potential mechanism by which a fertilizer shock could have lasting impacts. First, you have fertilizer shock resulting in higher prices, meaning that many farmers are going to apply less nitrogen than they otherwise would. That in turn results in lower crop yields, but also lower crop residue returning to the soil and replenishing the soil organic matter that also supplies a significant amount of the nitrogen to that year's crop. And if we get into that cycle where you have lower yields, lower residue return, and lower replenishment of that soil organic matter, it can create a long-lasting shock. So in the short term, the SOC helps to buffer the shock because the nitrogen within that SOC is part of the supply for the plant. But if that shock were to be sustained, let's say if there were infrastructure damage to the supply chain infrastructure for nitrogen fertilizer, you continue to draw down that buffer and see a feedback loop. We've seen this happen many times before, most recently in 2022 at the start of the Russia-Ukraine war. We saw that prices quickly doubled. The supply chain tightened, global nitrogen use fell, but within a year, markets normalized. We're seeing it happen again, and this time it's a different geography, but the same pattern: constrained supply, elevated price. We expect to see in-year yield response, but we don't know what happens after that. We don't know what happens in year 2 or year 3. So to explore that quantitatively, along with an economist at the University of Tennessee, Knoxville, Dale Manning, we built a coupled biophysical economic model. This model couples biophysical processes, agronomic yield response curves, and most notably an economic model that allows us to explore behavioral responses and system responses at regional and farm level. Obviously, this is a complicated model and we're not going to have time to get into it today, but more important than the details is the coupling. The feedback loop is what most fertilizer shock analyses miss. That feedback is fertilizer use changes yield, yield changes the residue return changes future nitrogen supply, and future soil nitrogen supply changes the next yield response. So this model allows us to explore that quantitatively. We're going to explore 2 different scenarios today, side by side. First, we're going to look at what happens with an acute shock, so a short-lived price shock, supply shock, that translates into yield and margin for the grower. And then second, we're going to explore what would happen if we were to see infrastructure damage that caused a long-term reduced supply of nitrogen. What would happen to soil organic carbon stocks over that time period? So here are the overall model predictions for those 2 different scenarios at the global scale. The model predicts that with a 100% price shock, which translates, a 20% supply shock, which would translate into a 100% price increase for yield in order to reduce the demand accordingly, would result in a global yield decline relative to baseline of about 4%. Now, if that price shock is short-lived, you get recovery, but not full recovery. The model predicts that you'd still see a decline relative to baseline from that 1-year shock that persists through time. And if that reduced supply continues over time, you'll see that initial 4% hit to global yield actually increases over time because of that compounding effect that we talked about earlier. So now let's zoom in to scenario A, the pulse. You can see here, we now are looking at the farm scale and considering within each region, if you have more or less soil organic carbon relative to the regional mean, how does that supply shock impact yield on any particular farm? So the effect is strongest in sub-Saharan Africa, and the buffering effect is weakest in North America, Latin America. Europe is very similar. You'll see in all regions that if you have less soil organic carbon than the regional mean, you have a higher yield change because less of your nitrogen is coming from the soil buffer. And vice versa. If you have higher than average soil organic carbon, you have a greater buffer and that yield hit is less. The effect is strongest in sub-Saharan Africa. There you'll see it's a 50% of the regional mean SOC. You have a 4.2% decline in yield versus 3.5% at the regional mean SOC. Now, that may not sound dramatic, that 0.7% gap between the two, but that's within region, within shock comparison. And as we'll see next, that small yield gap can translate into a much larger and really meaningful margin gap for the farmer because input costs stay high while output volume falls. So now this graph is looking at the gross margin change on a farm. Again, looking at it relative to the regional mean SOC within each region. So at regional mean SOC, gross margin falls about 12%. And at half of the regional SOC, about 16.5% in sub-Saharan Africa. So that spread is much wider. For a smallholder farmer that is financially constrained, liquidity constrained, that's about $20 per hectare. And that's really a big difference. That's the difference between being able to afford the next round of inputs or not. The reason why that margin gap is wider than the yield gap is because of price elasticity. So when fertilizer doubles and farmers cut back, input costs stay high, volumes fall, so margin compresses faster than yield. The previous slides were looking at the effects of a one-year pulse. Now let's think about that scenario B when we look at a sustained supply chain impairment that reduces the global supply of nitrogen fertilizer by about 20%. This shows where we land at year 10. The bar on the left is the global average, and you'll see that it's about a 5.9% decline in yield relative to baseline. And it divides that impact into the direct effect of the fertilizer shortfall, and then in the gold color there, the additional loss from the soil organic matter depletion. That's that compounding effect that we talked about earlier. So it's about a quarter of the total hit is due to that compounding effect that is the result of the depleting soil organic matter, essentially by mining the nitrogen out of that soil and not replenishing it at the same rate. And then on the right, you'll see that we've broken it down by 8 different regions. And again, sub-Saharan Africa has the strongest effect, and North America, Latin, Eastern Asia, and Eastern Europe have the smaller effect, although it's still important and significant. So soil organic carbon rich soils in this are less affected, but they're not unaffected. The buffer is meaningful in points of yield, but we're really need to focus on the margin hit because that's where farmers feel it. So the compounding effect over many years of a suppressed nitrogen supply would be detrimental to soil organic carbon in all regions, and especially in those regions on the left of the graph there. So now let's think about how that translates. So we've seen that at the farm scale, especially for smallholders in sub-Saharan Africa and other regions like that, it's a meaningful hit to their gross margin. It's going to affect livelihoods. The model, those predictions depend on a lot of assumptions, and one of the important assumptions is the elasticity of fertilizer demand. So we explored how sensitive the model is. And if we were to halve the price elasticities, that compresses the global yield loss by about 25%. So those numbers are important, and it adds some uncertainty to the range of estimates here. I'd say we should really focus on the direction and magnitude of the effect, and not we don't have the data to really parameterize the model with great certainty. But that translates at the global scale to about $47 billion just in that first year of crop value that's at risk. So about that's really significant, and it does back up the concerns that we see in the media around food shortages and probably more likely food price increases. So the results suggest that soil explains resilience within regions, and economics explains the exposure across regions. Here, what we're looking at is the link between soil carbon and nitrogen use efficiency region by region. So nitrogen use efficiency is where soil function, crop demand, and fertilizer management meet. Soil organic carbon can improve the soil supply side of nitrogen use efficiency, especially when paired with good practices like better timing, placement, and synchrony with crop demand. The pattern that emerges here is that a roughly 0.1 shift in NUE buys about 3 percentage points of buffered loss under shock. So the higher your NUE, the less you're going to see that shock impact yield and margin. The slope is steepest where soil organic carbon is lowest. So again, important benefit to having more soil organic carbon. NUE, though, of course, is more operational. It's something we can manage with technology, with good practices. So it's really a bridge between the soil science variable and something that agronomists, lenders, policymakers can address. So soil organic carbon is both an investment in nitrogen use efficiency and its downside protection. So let's think about where on the planet is most susceptible to the impacts of a nitrogen fertilizer supply shock. We'll look at 3 different layers. So this is the soil buffer layer of this screen. It's a cropland weighted soil organic nitrogen proxy built from soil grids, SOC, and C to N ratios, and weighted by where crops grow. So think of it as the supply side of the mechanism, where soils carry enough organic nitrogen to dampen a fertilizer shock and where they don't. On its own, it doesn't tell you anything about risk. A low buffer country with little reliance on synthetic nitrogen isn't really exposed. So that's what we'll look at in the next layer. So this is the exposure layer. So 2 metrics combined, the synthetic nitrogen intensity from FAO statistics and fertilizer import reliance from IFA trade data. This is really the demand side of the story. So where does production lean most heavily on synthetic nitrogen inputs, and how much of that nitrogen has to cross the border to arrive? Both matter because a country can be have intensive fertilizer use, but if it's domestically supplied, and if that supply is not reliant on oil exports or natural gas imports for production, it's less vulnerable. So the stock channel is strongest where both of those run high. This is exposure. It's not really vulnerability per se, but it's how much the impact would impact the demand side. And when we put those 2 together, we get a overlay that suggests which regions have the most exposure. So we combine the buffer and the exposure classification, and here we can see the regions that include China and Australia, and Brazil, Argentina, much of LATAM, as places where you have both low buffer and high exposure. Those are the areas that we need to think about the most. So this model has a lot of assumptions and parameters in it. So I think what's most robust in here is the direction of the impact. So soil organic carbon buffers shock effects within regions. Pulse shocks fade over time, but sustained shocks compound. And sub-Saharan Africa and South Asia are clearly most susceptible to this supply shock. What's less certain is the magnitude, the absolute yield and the margin magnitudes. Although I gave precise numbers, those are model outputs, and not we don't have enough data to accurately predict those. The translation into food security after trade and price adjustment. On the economic side of the equation and the policy side of the equation, there's lots of levers to pull and lots of unknowns to predict. so it doesn't translate directly into food security. But let's pull it all together. So soil organic carbon uh, really emphasizes how important the 4 per mil climate target is, and the additional benefits for nutrient and financial risk mitigation. So for farmers and agronomists, the message is building the SOC is really insurance for a bad year. And of course, it does have benefits every year, but it's especially important in when you see something like a fertilizer shock. That's where that investment in soil health really pays off. For lenders and insurers, this is a topic I'd love to talk about more. Um, SOC is an important variable in assigning or predicting agronomic risk. So risk of crop failure and therefore insurance payout or default on loans. So it's something that should be incentivized through in loans in insurance policies. And then for policy and people that want to support NGOs, SOC is more than just a climate buffer. It's also insurance and vulnerability for food supply and for farmers. So it's really there are multiple aspects of SOC. NUE is another lever that we can operationalize and manage. And SOC, building up SOC contributes to improved nitrogen use efficiency. So to sum up, uh, we started with a question today. We asked, when does the fertilizer shock actually end? And the model suggests it really depends on the soil that shock lands on. On soil organic carbon rich soils, that shock is better absorbed. On SOC depleted soils, the shock is amplified both at the farm revenue and margin level and carried forward through the crop residue cycle. Farmers protect margins, lenders protect price risk, and policy screens vulnerability. So SOC is climate value, but it's also nitrogen value and resilience value at the same time. The tools to measure that exist today, and together we can work towards making the value of SOC more visible and incentivizing and rewarding farmers to help to build that. Thank you.
Thank you, Matt, for the wonderful presentation. So we'll move on to our next speaker. Our next speaker is Stuart Grandy. Stuart is a professor of soil biogeochemistry and fertility at the University of New Hampshire. Stewart's research is mostly focused on soil organic matter dynamics, nitrogen cycling, and microbial ecology and agroecosystem resilience. So he is widely recognized for advancing microbial and biogeochemical understanding of soil organic matter, and his most recent focus is on bioavailable nitrogen. He was named a fellow of the Soil Science Society of America, and now he's going to tell us the role of soil organic matter. Over to you, Stuart.
Thanks, Booty. It's great to be here. I assume that everything technically looks good, or you would let me know. So I'm going to follow up on Matt's really interesting talk and dig a little bit more into sort of the mechanisms of nitrogen use efficiency, sort of go beneath the soil and look at some of the processes, the pools and fluxes in the soil that we might be looking at to increase NUE, and also looking at that relationship between NUE, soil organic matter, and the ability to buffer fertilizer shocks and the role that different organic matter pools might be playing in that. And just before I begin, I'd like to acknowledge that the work I'm going to be presenting today is it's an accumulation now of multiple years of work, and many students and postdocs have contributed to that. So thanks to all of them. Some of them are listed here, and there's, of course, many more. So we often think about fertilizer from the standpoint of how much gets into the soil. and how much then is taken up by the crop in any given year. So we really think about fertilizer as an annual problem. How much is applied, what's its cost, and how much of that fertilizer is taken up by the crop that year. And in some ways, that approach is really ignoring the role of the soil and the soil matrix. And fertilizer is not bypassing the biogeochemical matrix in soils. In fact, it becomes part of it. That below ground ecosystem includes the roots, the microbes, the fauna, these really complex mineral surfaces, organic matter, pores where there's air and water and living things. And fertilizer doesn't just operate independently, even in organic fertilizers, of this biogeochemical matrix. In fact, it becomes part of this matrix. And in some ways, that can be seen as a complication, something that we need to account for. But we also can think about this as a way to build that buffering capacity, to build up soil organic matter for those shocks. And so some of what we're doing when we apply fertilizer is we are replacing the exported nitrogen, and we are building up soil organic matter N to sustain fertility in future years, and also be building up different pools of organic matter in the soil that improve the resiliency of the system, not just to shocks, but different intra-season environmental conditions. And we talked about that in this paper that we published in 2022 in this diagram by artist Elena Hartley, where we see on the left, we have sort of a scenario where it's very low soil health. That system is highly dependent on fertilizer inputs. There's very few pools of organic matter to access. The life in the soil is not active. Aggregation is low. And you can see in the lower part of this diagram that that system is entirely dependent on nitrogen from fertilizer. It maintains a very large plant available N pool. And when that nitrogen gets shut off, that plant available N goes down and yields go down. That is a system that is entirely dependent on one source of nitrogen and is very vulnerable to fertilizer shocks. I think a lot of agricultural systems are just that scenario right now. Look on the right, you have a system that has built up organic matter over time. It has multiple different internal pools of nitrogen that plants can access under different conditions. They can be accessed under drier conditions, wetter conditions, warmer conditions, cooler conditions. So again, those are systems that are more resilient intraseasonally to climate variation, but also across seasons when there is a fertilizer shock. And if you look below, the plant available N pool is smaller. The nitrogen from fertilizer is only one source of nitrogen. There's multiple different pools and pathways by which these plants can get nitrogen. And part of the way that you attain that is by thinking about fertilizer applications as a means to both optimize yields in this year and for future years. So what I'd like to do is work through a scenario that's somewhat similar to the one that Matt did, or at least we're going to end up, I think, in a fairly similar place. So I played around with a very simple model of nitrogen fertilizer recovery. And I have 4 different scenarios here. Fertilizer inputs of 240 kilograms on the far left and 50% fertilizer and recovery. You can think about this as like a high yielding maize system, status quo system. We get into scenario B, 70% fertilizer and recovery, which is sort of the goal that a lot of farmers and companies are seeking to attain. We have 170 kilogram nitrogen input. Inputs are reduced, but you can look at the grain export and it's exactly the same. Okay, so you can see the grain export and the 200 yield and 70% fertilizer N recovery, much lower inputs. Then we get into a scenario of where we're actually going to be able to build organic nitrogen in the third scenario, and I'm going to show you how we do that in just a second. We've upped the fertilizer input just a little bit. Grain export is the same. And so we are using that extra nitrogen to build organic matter. And then we have a shock scenario where we've substantially reduced fertilizer inputs to 75, and we've been able to sustain yields through relying on that buffer that we've built in scenario C through the course of a couple years. So let's have a look at what this now how this might play out. So on the left, we're losing lots of nitrogen from the system, and we're not building any organic matter. When your fertilizer nitrogen recovery is this low, it's really, really hard to build soil organic matter nitrogen, even with such high fertilizer nitrogen inputs. When you improve fertilizer nitrogen recovery to 70%, and you can substantially reduce inputs and essentially have the same scenario, no organic matter building. We get into the third scenario. We've upped the fertilizer rate just a little bit. Now we are able to build organic nitrogen. And then in the fourth scenario, a shock hits. I did introduce a ryegrass to capture a little bit of that nitrogen in the fall. So we have a little bit of nitrogen residue coming in from the ryegrass. With 75 kilograms of N per hectare input, we are losing 40 kilograms of N from soil organic matter N. But that's under this, but we're maintaining the same yields, and we're burning up 2 years of organic nitrogen building under the third scenario. And so the point here is that if the shock scenarios are not persistent for an extended period of time, 1 year, 2 years, we can sustain that because we've built organic nitrogen stocks in our system over the course of several years. So we've built resiliency into that third scenario by building organic nitrogen stocks that we can tap into to sustain yields during those shock scenarios. Soil organic matter, I always like to remind myself of this. It contains thousands and thousands of kilograms of nitrogen per hectare to plant rooting depth. We can be using this to support our crop yields. When I think about organic matter, it's very helpful to separate it out into these different pools. We often think about mineral-associated organic matter and particulate organic matter. And particulate organic matter has a high C to N ratio. It's partially decomposed litter fragments. It's often associated with nitrogen mineralization, or I'm sorry, immobilization because of that high C to N ratio. But on average, it does turn over a little bit faster. MAM, or mineral-associated organic matter, it has a much lower C to N ratio. It consists of proteins and amino sugars. In the lab and in the field, it's often associated with nitrogen mineralization. That pool of MAM is where we want to store organic matter long term. We know on average it's more persistent, but we also now know that there's a pool of that organic matter that cycles very fast. Some of it is very, very old, hundreds, thousands of years old. Some of it cycles very, very fast. It's also, as you can see, in this stacked bar where most of the nitrogen in soil resides. And so we've been focusing a lot on what role can this MAM pool be playing in basically buffering fertilizer inputs and acting as a short-term reserve or bank account where we can be storing inorganic N for recycling and future use. So thinking about the recycling and uptake later in that season, but also across seasons. And so again, just to better explain this mechanism, MAM can be a short-term reservoir for recycling inorganic N and protecting it from loss. We think about this as nitrogen immobilization by microbes, so that's inorganic N going in, being immobilized, some of it. from those microbial necromass. We know this from all the work various labs have been doing on soil organic matter formation, that microbial necromass becomes mayam, so that fertilizer now becomes part of that mayam pool. It remineralizes because it enters this fast cycling pool, as Andrea Yilling and others have showed us over recent publications. And we have this sequence where we can be moving some fertilizer in through this microbial pool into the mayam pool, re-released through the activity of roots and microorganisms. And the reason I think that this is an exciting pathway to be targeting is that there are interventions. There are places for industry, people like Matt working in Syngenta, thinking about how they can be helping farmers through different kinds of interventions and the more basic research that we're doing. And we can be looking at a pathway like this and thinking, how do we encourage that sort of uptake of this inorganic end pool for short periods of time by microbes? And then how do we encourage and accelerate that remobilization of that nitrogen later when the plants need it? And again, this is based on our knowledge that we know that there is this fast cycling pool of mayam. It's a very, very large pool overall of mayam nitrogen. It's not inert. Some of it is quite resilient and persists for long periods of time. That's where our persistent carbon gets stored. There's another fraction of it that cycles quite quickly and is associated with these much looser bonds, much more loosely affiliated with the mineral surface, and nitrogen, like for example, amino acids and small proteins can cycle in and out of that. And Andrea and a team of co-authors very nicely showed this in a summary of available data that we know that the mineralization and bioavailability of mayam spans a wide range depending on the mineral type that's there and the type of nitrogen that associates with that mineral surface and other environmental conditions, and that there's also desorption that can occur abiotically as well as through biotic mechanisms. But that again, there's a vast range of cycling rates through that mayam pool. And I would argue that this is something that we're really just learning is what are the controls over how quickly nitrogen cycles in and out of that mayam pool, which is going to be really important to figure out as we move forward. And just sort of an example of nitrogen movement into mayam. This is my student, Emma Berg, who looked at the percentage of added nitrogen recovered in the mayam fraction. Going from left to right, we have fertilizer and then fertilizer plus root litter, and then fertilizer and root litter again, but in a low and a high soil organic matter condition. And so you can see under low soil organic matter that the addition of litter is really critical to boosting that fertilizer nitrogen recovery in mayam. And then in a higher soil organic matter condition, we get much higher amounts of nitrogen fertilizer moving through that mayam pool. The dark shading indicates what was easily chemically extractable. So it seems like about a third of the nitrogen that enters mayam is easily chemically extracted. So that could be a proxy for what plants might be able to access that year. And then in a follow-up study, my student Manjo Reiki has been looking at different rates of nitrogen fertilizer in the field, and she's been really interested in this mayam N pool is an early season nitrogen reserve. So we often apply lots of fertilizer with planting or before planting when there's not active crop nitrogen uptake. And that's the period that we're really interested in, is how do we move nitrogen out of this really vulnerable inorganic dissolved pool into a short-term reserve at the time of planting so that it will be there and be available later in the season when the crops are actively growing and taking up nitrogen. And so she used an in-furrow treatment of only 5 kilograms of N per hectare and then 2 UAN bands of 74 and 148. This has been done in collaboration with Ag Spectrum Company. And we have found that not surprisingly, the in-furrow treatment of only 5 kilograms of N per hectare produced very little to total dissolved N, much higher total dissolved N rates with the UAN 74 and 148. Again, this is, I think, an indication of the concern that arises with these at-planting fertilizer applications. Even a lower rate like 74, they're creating this huge pool of dissolved inorganic. And she then looked using isotope tracers at the movement of that nitrogen through the mayam and then into the crop. She found that in-furrow rate of just 5. There was a very, very fast recovery at V3 in maize in the mayam fraction, 10 to 15% for the higher nitrogen application rates. And then you can see the crop uptake from soil organic matter pools and fertilizer on the right. In all of these systems, including in the very, very high, with very high rates of nitrogen application, the crop is taking up a lot of nitrogen from the soil organic matter, and we can determine that using isotopes. But the uptake of nitrogen from that really precise in-furrow low application rate is much more precise. And so what we really need to be thinking about is how do we balance that need for inorganic N early in the season while reducing that pool of nitrogen that's really vulnerable to loss. And I think if we could figure out ways, through crop management, for example, to move more of that inorganic N that's applied at planting into a short-term pool, we'll see higher nitrogen use efficiency. And we saw some work, some similar results from Tim Bowles' work where crop rotation built up nitrogen in the mayam fraction, primarily in the less than 20 micron fraction. This is a crop diversity gradient on the x-axis and percent N in those different soil fractions. And you can see across this gradient, we built nitrogen in the more diverse treatments, and then we grew a crop in these different soils. You can see that where we built nitrogen in that mayam fraction, we had much higher shoot nitrogen concentration. I don't show this here, but using isotopes, we also determined that a much lower proportion of that nitrogen or that system was much less dependent on an external nitrogen source when we added it. And also, even under drought, we were able to sustain nitrogen uptake from those mayam fractions in the diverse rotation. And so as we move forward, what we're really thinking about is sort of integrating these mechanisms, the microbial biogeochemical mechanisms, the different pools of nitrogen in the soil, the phase of the crop, and then how we complement it with 4R management. And so we have early in the season nitrogen accumulation, and then the building of nitrogen pools should be focused on organic sources. And then we have 4R complementary management, which is targeted in placement fertilizer N, and then we can go across the season to that critical period where there's active growth and rapid nitrogen uptake. We want to see more cycling from organic matter into inorganic pools, and then crop uptake, and then once again in the fall, nitrogen recycling and retention. And just to tie it up, reducing nitrogen losses can sustain yields, build organic matter nitrogen in different pools, and buffer future nitrogen shocks. We should be thinking about the fate of fertilizer across seasons. Agroecosystem NUE is one way to do that, and it includes crop recovery plus soil organic nitrogen accumulation. And fertilizer N can be retained, stored, and re-released through micromineral interactions, what we call IMER or immobilization, mayam formation, and remineralization. And the interesting thing about this pathway is it creates intervention points for retaining nitrogen and releasing it later. Thank you.
Thank you, Stuart. Thanks, Matt, for the in very interesting presentation. So let's move on to have a bit of a discussion, and they're also answering some of the questions from the audience. Maybe if I can start, like whenever I talk about nitrogen use efficiency to colleagues in agronomy and colleagues working on nitrogen, the 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 questions always comes up with that we all know that we need to have a agronomic nitrogen use efficiency, but farmers usually manage risk, not manage efficiency. And as you say, Matt, this is not the first time. This is the several number of times where we have this kind of problems. But as you say, that maybe after 1 or after 2 years, then we go back to the same problem that the farmers tend to have extra insurance in putting extra nitrogen in the system. So how do you think that uh, what kind of yeah, how do we move forward from this?
Yeah, I think to start with, you're right, and I think Stuart made a good point that when we talk about nitrogen use efficiency, it's kind of a term that is generally used, but it's really important to define exactly what we mean, and for different purposes, we may be interested in different aspects of that. Farmer, one of the challenges in ag is that farmers are generally managing on an annual budget and worried about their profit in that year. Um, and if that's your focus, you're focused on how much of the nitrogen I'm adding this year ends up in my crop. But if you're focused on the long-term maintenance of your soil organic matter health and that pool of nitrogen, then you're thinking more about how much of that nitrogen I'm adding is either making it in the crop or into the soil buffer. And I think one of the fundamental challenges in ag is that tension between uh, optimizing for your annual profit margin and optimizing for long-term sustainability and soil health. I think we all need to find ways to work within that system to make those better aligned.
Do you have anything to add, Stuart, about nitrogen use efficiency?
No, I mean, I think Matt captured the main points. I mean, I think that we do have to be really careful about how we define it. And, we like to think about it as, again, this agroecosystem NUE because it accounts for the nitrogen that goes into the organic matter, not as a loss, but as a way to maintain long-term fertility, um, as a way to buffer these shock periods. But of course, it's hard, to justify or to sort of account for this economically, right? And I think I think that this is where, in general, if we can move that needle of nitrogen recovery in the crop from above 45% or whatever it is, there are papers suggesting it, give or take, it's somewhere in that range, 50, 55, 40, that there's a lot of opportunities to do things with that nitrogen that's not lost. And one of them is to build future nitrogen reserves. And so I don't think we have to think about this as an either or, right? We can both build nitrogen in the crop, sustain yields, and be preparing for future uncertain scenarios. And the key is just looking at that optimizing our management to get that NUE up from 50% to 70. I mean, that really is the key. Then it opens up all the other doors.
So,
The one thing that's universal across all definitions of nitrogen use efficiency is that losses are bad. So no matter what, anything we can do to prevent gas or leaching losses of nitrogen helps that efficiency and building up the organic matter as well.
Yeah, so yeah, I think that as both of you say that the building of the soil organic matter is not saying that you're not going to replace it with fertilizer, but you're building a more robust systems. Uh, but uh, but but the other thing is also that building soil organic matter is a longer term system. It's not a but the fertilizer shock or the fertilizer the loss of a fertilizer is much of a quicker system. So how do you think that we can balance this? Building this is trying to encourage farmers, trying to encourage landholders to build this long-term storage buildings, build this long-term resilience where they are more worried about the faster system.
I mean, I think it gets to the thinking about the leverage points in the system that would help farmers. It's one thing to sort of ask that question rhetorically, or I think every farmer would agree they want to build up their soil health. But that's why I brought up the topic of insurers and lenders and thinking about agronomic risk, because right now the way that lenders assess risk is they look backwards at your production history, and they look at that relative to other farms in your area, and they look at how consistent that yield is, and that's how they sort of assume your ability to pay back that loan, or what the insurance payout might look like. But it doesn't account for farmers that are actively trying to improve their soil health. So it's a lagging indicator, not a leading indicator. So that's one point in the system where if we could work towards creating the right rewards for the reduced agronomic risk that comes with building up soil organic matter, and that would then create a financial incentive for that investment. I think there's lots of other points in that system. So it's not really about it's thinking about, from the farmer perspective, how they look at their budgets and their operations, what's missing from that system, why are the incentives not in line. I think if the incentives were correct, then or not correct, but if the incentives were better aligned with the long-term sustainability and soil health, and reducing that agronomic risk and building up yield resiliency, the farmers would follow that. And I think there are reasons why, even when they want to, the incentives just aren't aligned and motivating those choices.
And I'll just add to that. I think that was a really nice sort of broad, big picture perspective. I think, we're really focused in our program here on sort looking at the mechanisms that underlie this efficiency. And I don't think we're there yet. And so one of Matt's colleagues, Jordan Wade, is often asking me, when are we going to get this to a predictive place, right? Like when are we going to be able to better understand the internal biogeochemistry to a degree that it's a little more predictable? And I think that, that's where we're headed. It's just, it takes time, right? And so we have to be, from the standpoint of a, scientific community, be willing to, continue to make gains in our, fundamental understanding of nitrogen use efficiency. But as I said, I think we also have a responsibility to be attempting to link it to interventions and ways in which we might be able to manipulate those internal mechanisms to improve NUE. And that's why, we really are focused on that one pathway, right? Because we see this potential for interventions on both ends of it. It's hardly the only one. There are lots of places in the soil we can be focusing on for NUE, but there's still lots of work to be done.
Okay, thanks, Bruce. So we'll take a few questions from the audience. Ted is there's a question for Matt that he says that it's interesting that the regions that seem that most sensitive to price or supply shocks are also where we think smallholder farmer, smallholder integration of crops and livestock might be most useful. So, and he's asking that in your model, could you also incorporate alternative nitrogen source such as manure and other things to decrease the sensitivity to shocks?
Yeah, thanks, Todd. In fact, one of the reasons I wanted to build this coupled economic model is so that it allows exploration of those different behavioral responses in terms of shifting practices. We could both build that in into the soil mechanistic model, but also into the economic model. So yeah, I think that's something um, I'd really like to explore, especially for the longer term scenarios. There's a lot of other questions, related questions we could ask with the model, and I think that's an important one. It's important to when you think about something like livestock integration and manure management, to look at it not just at the farm level, but at the whole system level. And especially for manure, make sure you're tracing where that nitrogen is coming from, and it's not just moving it from one place to another, because it always pencils out well on the farm where you're adding it. But you have to make sure you're looking at the whole system level.
Okay, and Abderrahim first, there's a question for Matt. He's saying that early mineral and application it's really important. That is also what they observe in the Zimbabwe. So it's then he's asking you a question that is what is the weather rainfall condition considered here? Should that change the scenario if there's a nitrogen cycle in the nitrogen cycling if there are prolonged drought or heavy extreme rainfall?
Yeah, was that for Stuart or for
Oh,
me?
sorry, it's supposed to. Yes.
I was looking forward to your response, Matt. Um, I think those scenarios absolutely, the specifics of individual sites and regions obviously have to be factored into um, local fertilizer recommendations at the field scale. I wasn't really thinking about any particular sort of water regime. Probably the lens through which I developed that scenario was a Midwestern US maize system. I think the model that Matt is using is probably uh, would be better able to capture precipitation. The scenario I developed was quite simple. It was really a thought exercise, in part to prove to myself that what kind of work could be done with the nitrogen that we save when we improve NUE.
Maybe the next question from Jonathan to you, Stuart, is about the nitrogen recovery from MELM. So he's asking, uh, is it is how generalized is it? Is that it can be scaled across different soil environments with a different microbial or soil types and so on?
Yeah, thanks for asking. And we're asking those same questions. We've studied this movement of nitrogen fertilizer in the MAM across a lot of different soils. And again, depending on the mineral types and other kinds of carbon available, and we'll often see, from 10 to 40% of, high rates of N going into the MAM pool. The recovery is our understanding of the recovery is still coming. Andrea Yilling's 2025 paper does a really nice job providing an overview of all the mechanisms that release that nitrogen once it goes into that MAM and pool. But there's so little work that has been done on this. In part, it's experimentally quite difficult. We've now resolved some of those methods. We have a system for looking at plant recovery of meiomen, but we're really just headed down that path. The mechanisms are all laid out. We know it happens, but to get to a place where it's more predictive, we just are a few experiments away, I think. And yeah.
Okay, thanks. And maybe the last question, one more question is, I think this one is for Matt, is that what do you think about the novel fertilizer like nano or slow control nutrient release fertilizer? What are their roles in this kind of system?
Yeah, it's interesting to think about it in the perspective of the framework that Stuart presented, because it's a solution to a small part of the problem, and it's not really um, embracing the paradigm, I guess, of MAUM and nitrogen storage on the soil. So and they've been around for a while, so I think there's
Mm.
some plenty of research to look at in terms of how effective they are, and also adoption rates by farmers. But I guess I would suggest they're one tool in the toolbox. But I think what the new paradigm of nitrogen cycling in soil and agroecosystem suggests is there are a lot more levers to explore. So that's one that might be useful, but I think there's many more, and that's where my attention is focused, and I think a lot of others is considering our how our understanding of the nitrogen cycle has changed. What are those other intervention opportunities, both in management and also on the technology side?
Thanks. So we are almost run out of time, but so I'll ask a closing state question to both of you. So how do you see that the future of resilient food system look like? Do we ever have a low fossil input system, or is it impossible?
Hmm. I guess a couple aspects. I mean, a low fossil fuel driven system might be possible as alternative production for so green fertilizer arises. I think that's going to be a long development and adoption cycle to get it at economic parity. But that doesn't, even if we were to do that, if we were to have more renewable based fertilizer production, it doesn't solve the other issues around nitrogen fertilizer impacts. I think at the end of the day, we have to replace the nitrogen we're taking off the farm with fertilizer or organic additions. We just can't get around that basic rule. But I think that our new understanding really points to a lot of opportunities to improve the efficiency and prevent the losses that are so detrimental.
Stuart, do you think we ever have a low fossil fuel input system for agriculture?
I think it's always going to be about uh, tailoring management to local and regional conditions. And there might be across the board opportunities to lower dependence on fossil fuel inputs by improving nitrogen use efficiency. And some agroecosystems through diverse nitrogen inputs, might be able to wean themselves off fossil fuel forms of fertilizer. Others, that's going to be really, really hard to pull off. I think that the key is just going to be really not looking for a single solution, but understanding what's happening in our soils in ways that we can start to think about how do these mechanisms play out under different conditions, and how can we optimize management under those particular conditions. And that's going to look different across the globe.
Okay, thanks to both of you. Yeah, so we still need to understand more there. I think, as you said, that there are more levers that we can still optimize in the production system, and also and sort of building soil organic matter is one of the probably easiest or for the lowest hanging fruit that we can take for building a more resilient system, not just for climate but also for nitrogen and fertilizer shock. So thanks to both of you, and thanks to the audience. And the recordings will be made available, I hope, very soon, and then we can share with everyone. So thanks, everyone.